Hey everyone, welcome to Neural Notes, show where AI comes alive. Smash that subscribe button and ride the innovation wave.
Hey everyone, and welcome. You ever wonder how we actually measure change over time? Not just in a single split second, but, on average. Well, today we are going to break down one of the most fundamental ideas in math that does exactly that, the secant line and the average rate of change. Trust me, it's a huge building block for understanding pretty much everything.
All right, so here's our game plan. We're going to start with an idea you're already familiar with, then see what it looks like on a graph. After that, we'll get into the simple formula behind it, and then, the fun part, we'll use it in a real-world scenario. We'll even talk about why units are so critical before I set you loose to try one yourself. Let's do this.
Okay, so first things first. We're going to connect this big math idea to something you have absolutely done before, probably without even realizing you were basically doing calculus. So, think about this for a sec. You take those 200 miles, divide them by the 4 hours, and you'd get 50 miles per hour. Simple, right? Well, that calculation, that's exactly what mathematicians call an average rate of change. See? You've been doing it this whole time. It's just the total change in one thing divided by the total change in another. Okay, so that whole road trip thing makes sense. But what does this average change actually look like when we slap it on a graph? Let's take that idea from the highway and see it visually.
Now, don't let the word secant throw you off. It sounds kind of fancy, but the idea is super simple. Imagine you've got some kind of curve on a graph. You pick any 2 points on it, doesn't matter which ones, and the straight line that connects them, that is the secant line. That's it. It just cuts through the function in 2 spots.
All right, so we've got the line. We can see it connecting 2 points. But how steep is it really? How do we stick a number on that average change we're seeing? Well, we do that by calculating the slope of that line.
And this, right here, is the key to everything. This formula might look a little intimidating, but it's just the classic rise over run you learned back in algebra. Seriously, the top part is just the change in the vertical value. How much it went up or down. And the bottom part is the change in the horizontal value, how far it went across. This little formula is what gives us the average rate of change between our 2 points.
All right, theory's great, but let's put this thing to work with a real example. We've got a function here, the square root of x plus 1, and we want to find the average rate of change between x equals 3 and x equals 8.
The process here is actually pretty straightforward. First, we just plug our x values, 3 and 8, into the function to get our 2 points. Then, we just pop those points into our slope formula, the change in y over the change in x. And as you can see, a little bit of simplifying gets us to our final answer, 1/5.
So that's cool for just, a random function. But where does this stuff actually show up in the real world? Let's take a look at a business and its sales data. Check this out. We've got some sales data for Ryan's board game emporium. The table shows us how many games he's sold year by year. Our job is to figure out the average rate of change in his sales from when he started back in 2010 all the way to 2016.
Now, here's the cool part. Just like before, even with all this data, we don't need all the middle stuff to get the average over the entire time. All we need are 2 points, the very beginning and the very end. So point 1 is 2010, 512, and point 2 is 2016, 2612. Okay, let's crunch the numbers. We take the change in sales up top, 2612 minus 512, and the change in years on the bottom, 2016 minus 2010. That gives us 2100 divided by 6, which gets us 350. Great, but 350 what? 350 potatoes? 350 light years? By itself, this number is totally useless.
And that question right there brings us to something that is so important, but people forget it all the time. The units. Units are what turn a boring old number into a story, into a real insight.
The rule for figuring out the units is actually dead simple. It's always the units of your output, your vertical axis, divided by the units of your input, your horizontal axis. Remember our first example? It was miles on top, hours on the bottom. That gave us miles per hour. So let's go back to Ryan's shop. The output was board games sold, right? And the input was year. So that means our answer of 350 is actually 350 board games per year. Now that tells us something. It means that on average, his sales were growing by 350 games every single year for that whole period. That's a really powerful piece of info.
Okay, you've seen me do it a couple of times. Now it's your turn.
Let's see if you can put these new skills to the test with one last problem.
All right, here's the challenge. A plant's height in centimeters is given by the function h of t equals t squared, where t is the number of days. Your mission: find its average growth rate between day 2 and day 5. Seriously, hit pause, grab a piece of paper, and see if you can work it out. And don't forget the units. Okay, ready? Let's walk through it and see how you did. We follow the exact same steps. We find our 2 points at day 2 and day 5. We plug them into our formula, change in height over change in time. And that calculation gives us the number 7.
And of course, the final crucial step, the units. Our output was centimeters, our input was days. So our final answer is that the plant's average growth rate was 7 centimeters per day. See? The units make all the difference. They give the number its meaning.
So there you have it. We've totally nailed the average rate of change between 2 different points. But I want to leave you with a question, a big one that basically unlocks the door to all of calculus. What do you think happens to our secant line, this measure of average change, when those 2 points we picked start sliding closer and closer and closer together until they're basically sitting right on top of each other? What does that line become, and what does it measure then? Something to think about.